So I would like also to thank the organizer to invite me to give a talk here and to see people in presence, which is also nice, but it's already 1 year that we have people in presence in Italy, so it's fine. And I will try to use sharing, so in principle, you should see also the online people, the spot. And my talk will be...
Alessio, could you enlarge a little bit more the slides? It's showing up very small on my screen. Is it possible to make it larger?
If I turn the iPad, you see it?
Yeah, this is much better. Yeah, thank you.
You see, Luis is much more technological than me with the iPad, apparently. So the idea of the talk with respect to the one of Silke and Nir is not to be very precise, but to give an insight of the a topic that currently has been since a few years under research both on the theory side and on the experimental side here in Trento. Since many years we have the BC Center or INO-CNR BC Center in Trento, and so I hope to be able to give a flavor, not enter too much into the details, but rather to show what is possible to do with the new experiment of Gabriele, who is in the audience, and Giacomo Lamporesi and Alessandro Zenisini, that there's still also on the theory side a number of things to be understood, and that this system is capable to both stationary state that are interesting, but also out of equilibrium physics that seems to be quite remarkable. So, but since already Nir and other people gave a little bit of introduction on cold gases, so I can be very fast on the first part. What I need to remind you just we are talking about Bose-Einstein condensate, which means that we have atomic species that are bosonic concerning the quantum statistics, and therefore at zero temperature they will, so to say, occupy the same state, and in a pictorial symmetry breaking point of view, we have that the field of the bosonic field is replaced by a complex number, and nicely as Nir shown, now it's really possible to have this mapping because of the box. I took one of the first experiment by Zoran in Cambridge, so it's really possible to have a nice homogeneous system where all the particles, let's say if you have a non-interacting gas, essentially all the particles are in the k equals 0 state, and if you have a little bit of interaction, well, in the equation of state is something very easy. So with this 1/2 G is a coupling constant that I will remind you that Nir did already later, times density square. And if you don't have an homogeneous system and you want to study the analysis of the system, which is quite remarkable, is that it's possible to use the so-called Gross-Pitayevsky equation, which is a classical field equation which appear H bar, but is somehow the equivalent of the Maxwell equation for a quantum method dynamics. So this is the classical equation of a coherent field for the quantum field theory of BEC. And what is also relevant for people doing maybe nuclear physics or QCD is that the equation can be recast in a different form, which is called the superfluid hydrodynamic. And as you know, is the hydrodynamic that you called, I guess, a perfect fluid, which means that I have, okay, the continuity equation simply because I have the number of particles in our system is conserved. And the Euler equation, that essentially is the Newton equation for a fluid, where I also include an external potential. There is some quantum part, by means of there is an H bar. But what is important for me is to remind to people that these equations are not the classical hydrodynamics by means of collisional hydrodynamics, where a lot of collision equilibrate locally the system and make the possibility to use hydrodynamics, if you read in some books. This is really superfluid or a collisionless hydrodynamic. What keeps the system like behaving locally at equilibrium are not collisions, because strictly speaking, at equal 0, you don't have collisions, but it's really the coherence. And this is the basics of being possible in cold gases to do very long time experiment, because the collisional part is most cases not relevant, and you can use this kind of collisionless hydrodynamic. This is very well known, and what I just wanted to remind you, but Nir did already, that I have a clear potential between two atoms that can be of strange form, but since we are a very low temperature and very low energy, we are interested only in an expansion of the scattering amplitude to the first order. And if you have bosons, so we can just keep the scattering length and replace the real potential with an effective potential. And this is the coupling constant, which depends on the h bar, the mass, the relative mass, and the scattering length. As I said, in a formal way, you can see the BC as a system which break let's say the Yuan symmetry of the system, because once you select in the field a certain phase of the classical field, you select one of the phases, and thanks to the Goldstone theorem, you can say that, okay, in the excitation spectrum, you need to have a zero energy mode, because any phase of the famous Mexican art, this is the real part and the imaginary part, as many of you know, of the wave function, and therefore any phase here, any state here is equivalent, and therefore you need to have a gapless energy spectrum. And concerning the stiffness, what happens that instead of having free particle, you have a sort of sound-like excitation. What does it mean? That if you calculate the excitation spectrum of the system, is the famous Bogoliubov spectrum, which at low energy looks like linear. If you see, if you take the small q, you remove this part, and then you have this part here, and then it goes like c times k, where c is simply related to the equation of motion of the system. Now, if you, since my aim is to describe a coherent decoupled gas, what first of all I need is to have a mixture. The mixture is quite trivial. At the mean field level, I have the equation of state of the first component, the equation of state of the second component, and the interspecies interaction. Since in this case, both the particle in component A and the particle in component B are preserved, you have a U1 times U symmetry, and therefore when you condense the system, you are breaking two symmetries, and then you expect to have two Goldstone modes. Obviously, since the system is interacting, you don't have the sound of the component A and the sound of the component B, but you have hybridization. And in this case, let's take a case that is the two symmetric, so the interspecies interaction is the same. It's very trivial. One mode is an in-phase mode, the particles are moving together, A and B, and one mode is out of phase, which is the spin mode. And what happened that if the two species were degenerate, so they have the same spectrum, the interspecies interaction splits the spectrum into one is related to the density, as you see, it occurs the total interaction strength, and one is called a spin, which occurs the difference in the.
This Alessio, just one little thing. Can you press the done on the thing, because it's blocking some view of the slide? No, there's yeah, good, thank you.
Okay, good. I don't know if I find that yeah, okay. Every time that I touch it, okay. Well, in this case, Carlos, I'm sorry, I'm using the pointer as near. You will not see the pointer, but maybe it's better for you. So, however, now let's move to the real system that are interesting, which is a little bit more complicated. With not only have two species, but there is the possibility to have an interconversion term between the two, which, if you think in terms of electrons, is not too much of a problem. You apply a transverse electrical magnetic field, and then spin up and spin down can commute one to each other. In this case, you have really, for instance, hyperfine levels of atoms, and then you can convert one species to the other. The Hamiltonian, the quantum field theory Hamiltonian is the same as before. So we have the kinetic energy, some external potential, which can be spin dependent, the intra and interspecies interaction. And what you have now is that the possibility to convert the p atoms in A and vice versa. What happens is that now the symmetry of the system is reduced because you only conserve the total number of particles, and therefore you have only one U1 symmetry. For the sake of simplicity, I take that the system again is Z2 symmetric. It doesn't make so much a difference, but it's a little bit cleaner to explain the physics. And what happened that my order parameter, that is the wave function of the atoms, has to take into account the internal degree of freedom properly, because now you really have the whole block sphere to take into account, because you can really convert 1 into 2 and have SZ, SX, and Y and SY. So the order parameter now has a global phase that you are not very interested in, but then there is how much particle you have in, oh, sorry, I use up and down instead of A and down, sorry, and A and B, but the up and down are the two components, and a sort of relative phase. What happens now with respect to before is that I can write the equation of state in terms of density and spin density, which is the same as before, essentially, and just equation which is some constant times density square or spin density square. But what is more important is that you have an equation of state now that depends explicitly on a phase. That's not totally common to have. And having this, for people that are familiar to, it looks like a little bit a sort of, if you don't have density, a sort of sine-Gordon model, something that fixes the phase. And this is obvious because there is a laser fixing the relative phase between the two atoms, and this is what it is. But from the field theory point of view, this is a sort of mass for the spin. This is just some technical details. And what is also interesting for the system, as you don't have for the previous system, is that the ground state of the system is much richer than before. And this is the following. You can have a paramagnetic phase and a ferromagnetic phase. What does it mean? You can have a system, a phase, where all the atoms are pointing along the direction of the external field, which is my omega. Omega is converting one particle to the other. You go to the dress base. For people used to Bloch sphere, just going in the x direction of Bloch sphere, and all the atoms are simply pointing in the x direction and condensing. However, there is, you see, a sort of field which prefer or not prefer a magnetization, depends on whether it's positive or negative. And therefore, you can have a ferromagnetic effect. I would like to mention, but maybe most of you recognize it, but it's a T equals 0 transition. Therefore, it's a sort of rather quantum phase transition. And it's not a typical Curie ferromagnetism in temperature, but it rather are easing, what is called easing transverse field transition, which means it's really that everyone is pointing along X, and at some point in the Bloch sphere, all the atoms are pointing up. So this is my naive picture. I have, this is the magnetization, or if you want at Z, everyone is pointing along X, so are not blue or red, but are blue and red. And then, depending on this external parameter, you become ferromagnetic. And since we decide to have a Z2 symmetric system, both all blue or all red are equivalent. If you calculate at the mean field level the compressibility or the susceptibility of the system, you have the usual behavior of the susceptibility diverging at a certain point and the compressibility. I not discuss about this now, but the susceptibility diverges at a certain point, then you go from paramagnetic susceptibility to ferromagnetic susceptibility. So already you should see that this is richer, because not only I have the transition to the condensate, but within the transition to the BC, I have a possible Ising-like ferromagnetic transition. Now the question is basic, which is what are the excitation of the system? As I mentioned already, I have just one U1 symmetry left, and therefore I expect only one Gaussian mode. And as I show you already, for people used to field theory, you can interpret this as a mass of the relative mass, because only the sum of the particle is conserved, and therefore the dispersion relation is the following. You have a gapless mode, which is the total density mode, you have a condensate, and you have a gapped mode in the spin because you have explicitly blocked the symmetry. That's all. It's very easy. For people coming from quantum optics, it's clear. You're putting a laser, fixing the relative phase, and then you pay energy if you want to change the phase. What is interesting, however, is that if you include an interaction, at some point you cross the transition. You go from para to ferro. And this is typical. If you are familiar to quantum phase transition, there is this mode, which is gapped, become gapless, and then is gapped again in the other phase, right? As you know, in the disorder phase, is gapped in the order phase. At the transition, you have two modes that I would like to mention that are both linear. So I have both a sort of speed of sound, but only at this position. Obviously, the equation of whether this mode are very stable, the transition is not clear because you can have effect like a phone-on-phone interaction that at the transition can be very important, as in any phase transition, because the fluctuation are real. Now, what can be also interesting is to check the static structure factor of the system, because if you are familiar with many body theory, you know that the static structure factor, which means simply how well the system reacts to a certain probe, is in this case the density is trivial. It's always a condensate, and since the Bose condensate is the following, the Gaussian mode for the Bose is a phase mode, so therefore it does not react very well to a density probe. Now the static structure factor, as you know, is how well the system reacts to a density probe. Simply a small k, where the mode is a phase mode because it's the Gaussian mode, does not react. till well you realize that you have particle at very large scale, and then you react with a single particle. This is why it goes to 1. The spin mode is quite funny because does not goes to 0 and there's a gap. The gap is not a many body gap, but it's a single body gap. It's simply due to the fact that you have omega. Then you see that there is a sort of explosion close to the transition, and then something which is quite normal in the ferromagnetic, but this is trivial because then one component is very depressed, and then essentially you recover almost 2 independent components. But what is important is the extreme increase of the static structure factor at the critical point. And as I was mentioning, this is obvious because the spin mode is what is the driving force for the transition. And if you remember, the 0K static structure factor is related to the fluctuation of the system through the fluctuation dissipation theorem. Therefore, the zero moment of the static structure factor is just telling you that if I measure from experiment to spectrum, from shot to shot, the fluctuation of the magnetization of the system, the transition is diverging, which is what you expect, nothing better. But the nice point for me is that it's a really testable that you can analytically work out within mean field plus a little bit of Bogoliubov, but let's say within everything is analytical. It's very nice. It's a nice testable to explain people phase transition without going to complicated stuff. Now, here I show you the displacement relation. This has been discussed many years ago. Already in the 98 was one of the first paper described, not popular days, but was already included in these papers. But as an invention, till Gabriele and Giacomo decided to do the experiment. The experiment looks very nice, but it's very complicated because you have a magnetic problem here to deal with. And you need really to shield extremely well your system. And the people here in Trento, they really have an apparatus with probably more material around that really shield them. Okay, assume that you are very good to do it. Apparently they are. I trust the results. And so they decided to measure the dispersion relation. What we did to measure the dispersion relation, we say it's a bit not common. Usually people use Bragg spectroscopy and so on. We did Faraday spectroscopy. The Faraday wave, if you remember, is something that you shake a material to the frequency of the mode, and then you have a pattern, right? And this is called also Faraday pattern, and has been seen in many, many systems. Because this was much easier for our system. And there is also a problem of access, optical lens to have the flash of Bragg. And Bragg is easy if you want to have large K, small K can be a problem. And at that point, Luis says for fun. So, honestly, you have a nice system which is not linear. We know very well how to shake. In our case, the shaking was simply to squeeze. The system is a little bit like one-dimensional. You squeeze the transverse degrees of freedom. You couple, you have a frequency of the squeezing transversely, and at some point you really see that the system react, and then you see here, Gabriele was squeezing, not Gabriele only, but the computer somehow was giving the signal to squeeze it at a certain frequency. The condensate was completely flat, and then you see the pattern in either the density or the spin. So this was really for fun, and it was really nice to see this, and this is better for a non-homogeneous system. Because we have an harmonic trap, we are not at the moment, but we will do, I'm sure, with the DMD to have a box like NIR, we don't have yet at the moment. But and what is nice that if you then plot the frequency of the modulation as a function of the momentum of the pattern that you observe, you find this nice, very clean spectrum. And what I can tell you that the straight line is just the mean field theory without any fitted parameter. Take into account a little bit that the system is not really one-dimensional, there is a transfer derivative. And what is also nice is that you see there are also, first of all, you see that if Gabriele puts omega equals 0, so there is no possibility to interconvert the particle A, B, you have a mixture. And if you remember, the mixture has two Goldstone modes, and then you see the density mode and the spin mode with a different speed of sound that is smaller for the spin than for the density. If you apply the interconversion term, you open a gap. People like Jacopo Carosotto that are very fancy in quantum field theory, they say you have a mass for the spin mode, so you can tune the mass of the spin, change the omega. Omega is quite easy. It's just Gabriele could not agree with me, but somehow it's just an intensity of the RF frequency that you apply. And then tuning the omega, you tune the mass from 0 to something which is finite, and it's nice you can tune the mass from something which is small, something which is larger. Another point that you see many other sort of lines, and this is not surprising because the theory of Faraday waves is known to be possible to be, we did the quantum theory, but it's true at the classical level because everything is quadratic. The theory of Faraday pattern is equivalent to Mathieu equation. Mathieu equation is a very nonlinear system, and as you can read in the first book of Landau-Lifshitz, exactly what happened that there are not only the general harmonic, so the resonance situation, but the subharmonics. And therefore, we plot the subharmonics, and all the lines that we saw, all the signals were coming from subharmonics. Fine, so we just show that our system is able to implement the Mathieu equation or the Faraday patterns, and that the signal to noise ratio was enough to measure both the main harmonics and the subharmonics. And however, in this way, we were able to show that although the system is finite and non really homogeneous, we can extract, analyzing properly data in the center of the trap, we can extract the spatial relation and tune the mass of the spin. How much time do you have? 8 minutes. Very good. Very good. So now I would like to do something, quite fast in this 8 minutes that I'm left with, which are more a little bit more complicated experiment to explain. But what is important, all these experiments are based on the following. Before I show to you that the single condensate is based on hydrodynamic equation, very trivial, Euler equation and continuity equation. Now we have a spinor order parameter. So you have the spins. What happens if you have the continuity equation, the Euler equation with more part coming from the spin. But what is more important, you have an equation for the spin. Now the equation for the spin is very interesting to me because this part is just the conservation of the SU2 current in Noether theorem. But then you have something like a source which breaks the SU2 symmetry. And why we break the SU2 symmetry? Because the intra and interspecies interaction are not the same. Therefore, we break SU2. And we apply an external transfer field, which has a preferential direction. Therefore, the effective field H here include the breaking of the SU2 symmetry due to the non-equivalence between up, down, down, and up-down interspecies interaction, and the fact that you are applying an external magnetic field, and therefore you break, by definition, SU2. What is interesting of this is that you can realize immediately that if you check this problem, if you are able to remove the total density and the total velocity, we are left with a very nice equation that is only for the spin. But this equation has been derived by Landau and Lifshitz many, many years ago, and is called indeed Landau-Lifshitz equation for ferromagnetism, which is very interesting because you can derive also starting from Heisenberg equation, the long wavelength limit. So it was a very interesting equation. Somehow you realize that therefore your system not only has this ferro to para, but it's even more, it's silly that all the dynamics, if you're able, I repeat, to remove the total density dynamics, you're able to mimic the Landau-Lifshitz equation. Now, not only this, but the Landau, because the Landau-Lifshitz has something that somehow, obviously for Landau-Lifshitz was not interesting, but if you remove the current, you assume that you're able to remove the spin current, you're left with a trivial equation. It looks trivial, but this equation is the Josephson equation. So you have not only the Landau-Lifshitz equation, but if you're able to have a very nice system that includes as a part the so-called Bose-Josephson junction effect that I don't want to enter in details, but for people working in cold gases is known to have been quite well studied. Okay, these are an internal study Josephson junction, and the fact that the equation is absolutely non-linear because there is this term, you see that the effective field is self-consistent with the Z component of the spin. This makes the dynamics non-trivial, and that just for fun I plotted for you. If if the interaction is very small, you have the oscillation, just a normal precession around the field. But if the interaction is strong, you have what is called self-trap. So the system, you try to modify the direction of the SZ, and it is impossible. And it's called self-trap regime. That, by the way, we have Andrea somewhere, Trombettoni, who is one of the persons that really studied a lot the Josephson junction. In this case, it's not a Josephson junction, it's an internal junction. But for us, was not this the point. We wanted, first of all, to show that our Josephson junction works also in an elongated system. I don't enter in detail, but I can tell you that yes, we can plot the local Josephson junction, like use local density approximation. Each point is doing its own oscillation. With this is important because in this way we can measure the experiment is not easy to fit directly the experiment with theory, but the Josephson is very important because it's a frequency. You can measure very well. So you can measure the parameter of the system that you are less familiar with directly from the experiment. Once you map out the theory, you can play with this. And the idea with Gabriele was the following. Okay, but we have a self-trapping regime and a non-self-trapping regime. What happens if they occur in the same system? There will be a region where you go from self-trapping to non-self-trapping to a region where it's in between. Now, if you are familiar with non-linear differential equation and with this kind of bifurcation, you know that are very similar to phase transitions. Therefore, there is a point at the transition that is called the point of critical slowing down. What happens? It means that this guy is rotating, self-trapped, this guy is rotating, but there is a point that is not moving. At some point, you cannot sustain this system. Therefore, the idea of having Landau-Lifshitz does not work anymore. Landau-Lifshitz by Mr. Johnson does not work because the system becomes completely unstable. You see, we tried to plot the Josephson equation, and you see that it's something very funny. So you have to simulate the full Landau-Lifshitz equation to see what happens. And the idea was, okay, we have a funny ferromagnet that is sort of ferromagnetic here, sort of paramagnetic here. In between, there is something. What happens to the domain? Can the system sustain this situation? The answer is not. What is generated? We don't know. We just find something quite interesting, a lot of waves, and this equation that we have to answer. What is generated at the interval? You break completely the junction. There are a number of waves starting, are completely, has nothing to do with the dispersion relation. This is really highly nonlinear waves. What are they? We don't know. They look very much like shock waves, magnetic shock waves, non-dispersive magnetic shock waves. If you measure the correlation function, looks very much as a quench antiferromagnet. Is really a quench antiferromagnet that the people in the lab are creating? We don't know. This is completely open, could be interesting to discuss. And these are not known in literature because the presence of omega make the system non-integrable. So there is no all the tricks I don't know, like Nicolas Pavlov studying a lot of this. So we don't know. So the idea that maybe you are generating some antiferromagnetic shock wave just by driving the system. So it's completely out of equilibrium. These are the people that are really, these are the people in the experiment, especially Alessandro, Arturo that did a lot, Giacomo and Gabriele are the leader of the group. And here the theory person that helped in different stages of the studies, Faraday or Alberto and Arco helped a lot in the Landau-Lifshitz start. Jacopo entered in the Faraday business, and more details you find in a recent paper that we published. Luis, how I'm doing with time? Great. So okay, I have 1 minute, and just to show something very fancy, to show this was completely mean field at the moment, but as Near and other people, maybe you know that now in the field of cold gases, and Giovanni Modugno will talk more about it, are doing is going beyond mean field. Yes, there was, sorry. So about the going beyond, what we did recently with the coherent couple system, and we shown the result with the group of Thomas Portuel, was to measure in the presence of the coherent coupling, the Lee-Wang-Yang correction, so the beyond mean field correction to the system. And this is something quite funny because, you know, the Lee-Wang-Yang correction or beyond mean field has a certain power law in density. This is given by simply dimensional argument. If you include the Rabi coupling, you have a length more. And therefore you can decide what is dominating. And in a particular regime, you can see that the mean field, the beyond mean field correction is splitted in simply a correction to the two-body interaction, which makes sense because if you have a coupling constant, a Rabi coupling, the general two-body interaction is dressed by the Rabi. So this is clear. But what is more interesting concerning the question that was asked before about 2 and 3 body, you see, you can create a sort of real three-body potential in the system just by tuning this. And what is interesting that Thomas showed, I'm a theoretician, so, but apparently for an experimentalist is good enough, the agreement, showed that this would be the 2-body and the dashed line would be the 3-body. Then we do the really Gross-Pitayevsky plus beyond mean field plus the noise experiment. And it seems that they really need both the correction, simply if you want correction to the scattering length, but also the three-body interaction to explain the data that they found. So, and just to mention that there is more, and since this is a quantum easy transition, would be very nice to go beyond mean field and to analyze the fluctuation, to analyze if really this is of the universality class of the Ising, and not mean field as we have at the moment. They approach to it because at some point it's the same. And you see that here you cannot distinguish these two points, but so they are compatible. They are more on the M cube. They're not fitting parameters, but as I said, I trust so they're very familiar with experimental data, so they trust them. So okay, so and sorry, these are the team for DIMA. The analytical calculation was done with DIMA, and then they did all the experiments. So thanks a lot.
Thank you very much. Questions from the audience? Be ready to adjust yourself from
Thank you. So very nice talk, Alessio. I'm curious to know a little bit more detail on when you have local Josephson stuff and you have a delta phi of x, let's say. So you are in a regime in which the spatial variance of the relative phase is larger than the error of the phase itself, I guess, no? So you have, I don't know, phi of x, which is a relative phase, this changing space. And
this, Andrea, I stop you because we don't know. We have not measured. So we simulated, but we have not measured Sx and Sy.
Okay.
So the phase between X and Y, that are what you are asking, what we know is this is just, if you want, Sz, so the polarization, and this is how it looks like. And you see that the frequency here is different from the frequency here.
Okay.
If you plot the data, if you extract the Kn and then you plot the theory, it turns out to be compatible. So it seems that you can use for a certain amount of time a local density approximation. It's like your equation, the internal Josephson, let's say the Josephson equation, with different charge versus tunneling energy locally, and it seems to work.
But if you, from experiments, you measure the error of the variant of delta phi is smaller, and smaller than the spatial variation.
This honestly, I don't know.
Okay,
I can tell you that in some cases so in this case I don't know. In this case I don't know. Sorry, we're not calculated.
And the curiosity is when you have this phase which depends on x. In this long Josephson junction, you have underlying a Sine-Gordon description that would work here, or
yes.
So when you have the next figure, you have a deviation which breaks Sine-Gordon description.
Exactly.
Like Pokrovsky-Talabov model, or
no. Well, for me it's very easy. It's just the spin current, because at some point you have a spin current here. Because when you write your equation for the Bose-Josephson, you don't have external degrees of freedom. And then there is a gradient in the spin, and the gradient of the spin is here. You see what counts in the spin current. This is the advection current. This is almost zero. What is important that you have the torque. The torque is the derivative, the spatial derivative of the whole spin cross the spin. And this is strange for me. It was already strange. Honestly, there is something. We first did this experiment, and then we did the second this Josephson, because it is clear that the current is important. The funny point that if the system is quite homogeneous, you don't need the gradient of the spin, because it enters in a funny way. The gradient crosses the spin. And therefore, here, however, it's impossible that this is not important. This would be your equation local, your Auguste, your equation, right? And then it's clear that here the gradient is huge, it's infinite. So the system, you cannot avoid to have the gradient, and therefore you have to really use the Landau-Lifshitz. I have not mentioned that this is a simulation of the Landau-Lifshitz. This is a simulation, this is the experiment, and this is a simulation of the the coupled Gross-Pitayevsky.
Oh, the curiosity is you have if you have a deformed sign Gordon to describe that.
No,
But we can discuss later.
no, I don't. I use the Landau-Lifshitz.
Alessio, I have a question on the end, the Li Wang-Yang bit. So it's something that I really never understood, or got confused. The thing that you actually after the prediction on the next slide.
Ah, the last, this one?
Yes. So the prediction is based on the modified Gross-Pitayevsky, right?
Let's see, this prediction, the dashed, is the analytical prediction of me and Petrov. You take an infinite system, you calculate the Li-Wang correction because we know the modes that Gabriele has calculated, you sum all the modes to get the Li-Wang correction with the proper renormalization, blah, blah. And then you get a very long expression. Then in the regime of the experiment, nicely, which is this regime here, in the regime with omega is quite larger than this parameter, you can expand you see, this will be the beyond mean field correction. There is some, you see, this is the usual beyond mean field. This is the correction due to the radical coupling. Then in the regime of the experiment, you can expand, and fun enough, you find that the lowest expansion is the two body. This is trivial. You are tracing the atoms, why they should interact like that. And then there is this with what for Thomas was very interesting because it's a cube. So it's a emerging three-body term.
Yeah, so it's not sort of modified classical field description. It's really ab initio beyond mean field.
If you want to call ab initio, it's Bogoliubov, and then I sum
yeah, exactly. But
yes,
it's not
yes.
a modified Gross-Pitayevsky when you pretend that it's just a wave function
it's
with
not
a
the one
modified.
that we unfortunately use for the polar gases.
Yeah, exactly.
That is even there is also an imaginary part, and
Yeah.
you pretend that it's right. No,
I see.
this is really before any collapse or anything. It's really that they were able to go to a region where this is almost zero, and you're left with a very nice beyond mean field. They had to measure. I have no time to explain. We can discuss if you want how to measure where this occurs. Measure some Thomas Fermi radius. Then, if you plot the Thomas Fermi radius as a function of omega, you find this. Then we needed some time to understand this, but it's really due to the experimental noise. You see, it's not extremely evident, but for sure you need this correction. This for sure. And apparently, even the N-cube would be nice to have an experiment where it can go to a different regime. But this was just to show that it's possible. There is another point. If you try to do the same experiment without omega, they were unable to do. Because the omega makes the system much more stable. Because there is the gap in the spin mode, and then you are safer with respect to any kind of phase separation or low spin mode. You know, the spin mode is very, you remember the experiment of Zoran. The current was completely unstable due to the spin mode. So they tried, and then without that, you have a bouncing effect without the omega. With omega, you remove all this effect, and this is why they were able to measure the Li-Wang correction.